Greetings and welcome to this video, which is the second in a series that analyzes the mechanics of a can crusher. Now, in fact, you should have watched two videos before this. One is about the statics of this can crusher, and that analyzes the forces on the can crusher. But then also I have a lecture on columns, and that should be watched before this as well. Or at least you should have some familiarity with the analysis of columns. If you do not have any, then you should go back to your book or watch my video. Now, I used a different design for a can crusher because it was easier to do the analysis. So mine looks more like this. And I have the forces coming down and up here. There are more forces here, but we considered this a fixed spot here, so any reactions could come right here, and the can would be placed where this red arrow is, and we move this up and down to show the crushing of the can. Notice that we have a mechanical advantage here of 5 to 2, so it's a 2.5 mechanical advantage. So if we put in 40 pounds here, we should get 100 pounds coming up. That should be able to crush our pop can. Now, I also showed the dimensions, and here we have the 100, the 150 again, showing the ratio of where the forces are, and that gives us that mechanical advantage of 2.5. But then I've got the cross section here of this member. Now, this is the member we're interested in. This is the column. So as we push this down, force comes up here and loads this column. My initial design is 10 millimeters by 3 millimeters, and we will see how that works out for us. Okay, moving on to the analysis side, I copied this over, and here we go. So please forgive my handwriting. It's still kind of tough on this tablet, but I hope that you'll be able to work with me on that. Okay, I find it usually very helpful to list down all the things that we are given and also our ultimate goal. What are we trying to find? So in this particular problem, we are trying to determine whether our design is going to hold up well enough. We're going to find our failure force. So if our failure force is less than the force that we want to place on this column, then we know that we're in trouble. Now, when we say failure, is it going to actually collapse? Well, I really hope not, but we need to define what we are actually looking for. So that is going to come up in a little bit. So what are we given? Okay, one of the most important things that we're given is the material. The material is 2014-0 aluminum. So this is low tempered aluminum. It's intended to be kind of cheap because this is a low risk design and we shouldn't have to put too much into it. So what else are we given? We are given that we have this diagram. We are given that our required force that we're trying to design to is 450 newtons. Now, one more thing we have to concern ourselves with is that we have two failure modes. And one is it failing in the x direction, and one is failing in the y direction. What do I mean by that? Well, we are going to define our axes here is the x direction, and this axis here will be the y direction. So I've put little arrows here. Now you can see that if this column moves and buckles by going out in either direction in x, then that's one failure mode. And if it goes in either direction in y and buckles in that direction, then we have to look at it from that perspective. Well, you might say, well, it's obvious it's going to go in y because it's much thinner in that direction. But there's another issue involved, and we'll have to take that into consideration as well. So that's what's given. We might have to remember another given or two later, so I'm going to write down what we need to look up. Okay, now we've got the material 2014-0. It'll look up its various properties. Its ultimate strength is 186 megapascals, and its yield strength is 96.5 megapascals, and modulus of elasticity is 72.4 megapascals. Well, where did I get that from? I went to that awesome thing called the internet. And if I go to ASM Aerospace, a supplier of this type of aluminum and many other types of aluminum for that matter, they give you all sorts of information on 2014-0. So here's my ultimate tensile, here's my yield, and my modulus of elasticity. A variety of other things they give you as well in case you need them, but we don't need that today. Now, a couple more things. One of the givens that came up is the requirement that we have a design factor, and in the textbook I usually call it N, and we're going to have an N of 4, which means that our design force of 450 newtons, we should have a design that will withstand 4 times this amount before it actually collapses. So now that we've got that, and we've looked up some of the properties of our material, and we need to, I want to make sure that, I want to show you why we need to consider both the X and the Y. It's because when we look at this design, the links here are pinned, but they're only pinned so that it can rotate in one direction, in our case, back and forth in the Y direction. But here, it's kind of held right there in place in the X. So we have 2 different ways of fixing the ends. So our end fixity factor, K, is going to be different whether we're looking at it from the X direction or from the Y direction. So that is going to affect our analysis. And that is why we have 2 modes of failure to look at. Okay, so our problem is set up. We know what we're looking for. We have our requirements and the key things that we have to consider. So we've got the axis of motion and our design factor. So let us look at it first from an XX point of view. Okay, before we go any further, I need to make a correction that that's going to be 72.4 gigapascals, not megapascals. Okay, well, speaking of our material properties here, we should go ahead and calculate the column constant. Column constant is based on material properties, and we're going to use it a lot in any column problem, so we may as well just calculate it right off the bat once we have these things fresh in our mind. So the column constant formula is 2 pi squared E over the yield strength, all under the radical sign. So we take the square root of 2 pi squared times 72.4 gigapascals all over 96.5 megapascals. And we end up with a column constant of 121.7. Now notice that we have gigapascals divided by megapascals, so that's just 1,000 megapascals, so the units all cancel out, and so this is 121.7. It's unitless. Okay, so that's what we're going to use for 2014-0 aluminum alloy. Okay, so each column constant is going to be associated with a particular type of material. A couple other formulas we're going to use is we're going to compare the column constant to the slenderness ratio. The slenderness ratio is K times L over R, and K is the fixity factor. We're going to talk about that in a second. L is the overall length between supports, and R is the radius of gyration, which is calculated from the cross-sectional area here. And that R is the square root of I, the area moment of inertia, divided by A. And the area moment of inertia, I, for a rectangular cross-section, is base times height cubed over 12. Now, that is about the x-axis. So that would be Ix, whereas Iy is going to be hb cubed over 12. And since that's different for I and x, then R is going to be different depending on which one you use. So let's define our base and height here. 10 is our base, and 3 is our height. Okay, now that we've got that down, we're not ready to calculate any forces yet. We got to do some more analysis on this first, setting all these values up. So we're going to first look at what would it take for this to fail in the XX direction. So it's going to be pinned. If we have failure, buckling in the X direction, what do we do? Okay, so we need to calculate some of these things. We already did the column constant. That won't change depending on which direction we use, because it's all about the materials. But the slenderness ratio is going to change depending on R. R is going to change depending on I. I is going to change depending on the direction we're talking about. So let's look at this. If we're going to do failure in X, going back and forth in X, that means we're going back and forth across the Y. So we need to find IY. IY is going to be HB cubed over 12. H being 3 millimeters, B being 10 millimeters, cube that and divide all that by 12, and IY ends up as 250 millimeters to the fourth. R requires the area. Area is going to be the same for both. So area should be simple. Area equals base times height equals 10 millimeters times 3 millimeters equals 30 square millimeters. Now we've got I and A. We can calculate R. R across the y-axis is square root of I over A, and that is square root of 250 millimeters to the fourth all over 30 millimeters squared. R ends up 2.89 millimeters. So that's the radius of gyration. Okay, next, we built this up to the slenderness ratio. This is key here. So our slenderness ratio is K times L over R. Now our K, should have mentioned of that, K is 1.0 because it's pinned. That gives us 1.0 times L. L is another given we did not mention here. L is 200 millimeters. That's from the diagram from before. So here's the 200 millimeters right here. So 1.0 times 200 millimeters all over R, which is 2.89 millimeters. And again, millimeters cancel out, and we have a unitless number, which is 69.3. So now what we want to do is we want to compare the slenderness ratio of 69.3 to our column constant of 121.7. If our slenderness ratio is less than the column constant, that means that the failure mode is going to be dominated more by properties. But if it's greater, that means it's very slender, and our failure mode is going to be dominated more by the length and the radius of gyration. So we compare, and SR is 69.3, and that is less than 121.7, which is RCC. So therefore, we call it intermediate. And if it's intermediate, we use the J.B. Johnson formula. The J.B. Johnson formula tells us that the critical force is equal to the yield strength times this mess, 1 minus the yield strength times the slenderness ratio squared all over 4 pi squared times the elastic modulus. And because we're looking for the critical load, we multiply this times the area, plugging things in. We have the yield strength equal to 96.5 megapascals. What's inside here is 1 minus, again, 96.5 megapascals. SR, we calculated as 69.3 squared, and that's all over 4 times pi squared times 72.4 gigapascals, and then multiply all that times the area, which is 30 square millimeters. And once that is all taken care of, end up with 2426 newtons. So since that's a critical load, and that load has to be at least 4 times what we actually want to put onto the can, we need to take this and divide it by 4. So we find our allowable load is the critical load over n, and that's 2426 divided by 4, and our allowable load ends up being 806 newtons. Since 806 newtons is greater than 450 newtons, this works. Okay, but then again, that was only in the XX direction, which we actually figured, maybe it's not going to fail that way because in the YY direction, it's much narrower. So we'll have to look at that next. Okay, now to look at failure in the YY direction. This is the way we assumed it was going to fail just from looking at the cross section, but remember the connection may make a difference. Now, if we consider that it is fixed in that direction, here's our chart again, and if it's fixed here and fixed here, theoretically our K value is 0.5, but on a practical level, we want to use 0.65 to be safe. So that's what we're going to use. So fixed, K equals 0.65. And we will go through a similar analysis here. So Ix equals BH cubed over 12. And that is 10 millimeters times 3 millimeters cubed, because we changed axes. We're going the other direction now instead of this way. So we change our H and our B. Divide that by 12, and you get 22.5 millimeters to the fourth. Notice how it's much less than the other one. Okay, so our area, as we already said, is 30 square millimeters, and that gives us an R about the x-axis. Ix square root of 22.5 millimeters to the fourth, all over 30 millimeters squared, gives us 0.87 millimeters. So now we can calculate our SR, and our SR is done similarly. We've got K times L over R, and that gives us 0.65 times 200 millimeters, all over 0.87 millimeters, and that is 150.1. So we go through and we compare it to the column constant, and it is greater than the column constant, which is at 121.7. That means that it is long, and that means we use the Euler method. And the Euler calculation for the critical load is pi squared EA over the slenderness ratio squared. So pi squared times 72.4 gigapascals times 30 square millimeters, and our SR is, make sure you use the correct one, 150.1, and that's unitless. So when all is said and done, we're taking gigapascals, multiplying by square millimeters, and we'll have 1,000 newtons, or a kilonewton. I prefer to put it all into megapascals. So gigapascals, millimeters. So I'm going to multiply this times 1,000 newton. So if I multiply all this out, I end up with a critical load of 951 newtons. And if I consider my design factor, my allowable load is my critical load over N, and that's 951 newtons over 4, and that yields 238 newtons. And since that is less than our required, then we do not have a good design. What this tells us is exactly what our gut said over here, was that this is going to buckle somewhere in the Y direction, and it's going to do it well before 450 newtons. So we need a new design. In review, we started off with a statics analysis of a can crusher and determined the force that is going to be on this column. And we have a cross section of the column here, and we need to find out whether this force that's going to be on it is going to be doable with the materials and the design. So we're given the material and given a design factor here. We were already given the length from before. We looked up some of the material properties and calculated our column constant, our CC. Now this is going to help determine whether this is going to fail because it's too long or too weak. So we used our slenderness ratio, our radius of gyration, and the definition of that using the area moment of inertia for a rectangular piece. And we calculated all of these things and determined whether they were intermediate or long, depending on which direction that we expected the failure to occur. And based on that, we used two different models of how it would fail, and we calculated that critical failure force. And for failure in X, we ended up with an OK value of 806 newtons, which was greater than our design value of 450. But in Y, it was too long, and it was expected to fail at much less than the 450 newtons. So we need to redesign this. Now this video is long enough for the moment, so I'll do one more video that shows a redesign of this, coming at it from a different perspective. So make sure you watch that as well. All right, well, I hope this helped you understand the analysis of columns better. And again, stay tuned for the next video to finish this up. Thanks for watching.